Hi all, welcome to the 24th seminar of the India seminar series. Today we got Dr. Dinesha Hegde, who's a research associate at Center for Space Plasma Physics at University of Alabama in US. And basically today he's going to present Magnetohydrodynamic modeling of the solar wind with quantified uncertainties with multipoint validation in the inner heliosphere. And Dinesh, over to you.
Okay. Thank you all for the opportunity, and let me start. So, yeah, I work on MHD modeling of the solar wind and simultaneous quantification of the uncertainties, as well as multi-point validations in the inner heliosphere. So, uh, these are my collaborators and advisors. So, I should thank them for the support. So, okay, so to start the solar wind and space weather. So, as we know, how solar wind is driving all the drivers of the space weather, basically like coronal mass ejections and associated SEPs, as well as the time-dependent structures like stream interaction regions, so which can cause the geomagnetic storms. And the interaction between solar wind and coronal mass ejections can determine its path or just the destiny of the Earth. So this is a very important component of the space weather. So if we get the solar wind correct, then all other transients can be modeled better. And so this is a essential part of the space weather. So this is just a motivation to study solar wind, maybe, but uh, where are we in terms of modeling the solar wind? Like, as we know, like the modeling solar wind involves a modular approach, because the level of physics or the computational complexities and the observational uncertainties decides our approach to model the solar wind, starting from Parker's approach to model the very basic assumption. Now we have come so far, like with the very sophisticated models like 3D MHD models with data-driven simulations. So as you can see here, the space between Sun and Earth can be separated into three regions because of the computational approaches. So basically, we start with the photosphere, where we have the best observation about at least one of the component of the MHD variables, the magnetic field, and then the corona and the inner heliosphere. So whatever may be the approach, even with the fully physics-based model or semi-empirical model or even the machine learning model, so one has to deal with these domains. So this is a overall the physical domain we are dealing with, and but we have come so far with multiple models and sophistications, but where are we actually? Although this paper is like 10 years old, so the limitations of current models still exist, because other than the drastic change in the computational capability and the efficiency, like nothing has much changed after 2015 in terms of observations to um, aid in our simulations. So what this paper says is basically all the CCMC models were compared against Earth observation, so to understand the relative performance as well as so their strength and the weaknesses. But what happened was none of the models consistently outperformed the others in reproducing all aspects of solar wind conditions at Earth. So that shows that, of course, we are missing a lot of things, but uh, how to deal with this, still we are figuring it out. So we need better models, better validation strategies, as well as better boundary condition handling. So this is an ongoing issue with the background models. So, but what are the challenges do we have, to be frank? Like although we have state-of-the-art models, highly efficient, fully physics-based models, or highly efficient, at least semi-empirically driven MHD models. Right now, as we know, okay, WSA and LIL model is operational due to its computational efficiency, as well as its vast application in terms of inner heliosphere. But still, we are using the photospheric boundary conditions not in a very time dependent fashion. So that means like we need the global photospheric maps even with the small temporal cadence rather than 27-day due to its importance in solar dynamics. As we all know, like within 20 days, within 27 days, a lot of things changes, and that affects the inner boundary, and so in the corona, and that affects the solar wind. So that's why the major uncertainty is coming from the photospheric boundary conditions. Although we have surface flux transport models of various capability nowadays, we are not we are not able to solve this issue because we are totally missing the solar far side magnetic field measurements. So what happens is, in the far side, if some active region just appears, then we will not be able to get its polarity, and the location is possible right now, but the polarity accurately as well as the distribution. So this sudden appearance of active regions can affect your coronal solutions drastically. So this is an important issue. At the same time, we have a large uncertainty near the limb. So depending on the time of the year, so we might get a polar magnetic field measurement, at least only one pole of the sun, but others will be lost. At the same time, we have the uncertainty near the limb, as I mentioned. So this will affect a lot because these polar magnetic fields control the heliospheric current sheet. So that determines a lot of stuff near the equatorial region. So we have some challenges, but to address this challenge of uncertainty in the photospheric boundary condition, until and unless we do the observations of far side of the poles simultaneously, we will not be able to solve this issue anyway soon. But the only way is to quantify this uncertainty and try to reduce it or live with it. So that is the purpose of this project, basically. So, but how do we do this? Like uncertainty quantification in weather domain is very famous in terms of ensemble modeling. In their case, basically, the whole system is determined by the initial condition uncertainty. So that drives a lot of stuff in the weather domain. So for them, the ensemble comes from the initial condition uncertainty, and when they advance in time, so the model uncertainty will be forecasted. So basically, this is the typical approach in their domain. But in our case, the time domain shifts to space, and the initial conditions shift. So in the boundary conditions at the corona or in the photosphere, and the forecast uncertainty can be model uncertainty. So, and the forecast uncertainty can be also obtained. So this is a typical approach. We learned from actually weather domain. So I want to apply the same approach for my study. So basically, the objective of this whole study is to simultaneously validate and quantify uncertainty in our solar wind models using multi-point inner heliospheric observations, motivated by multiple spacecraft available right now with spacecrafts like Parker Solar Probe, solar orbiters, which give advantage of like various heliocentric radius, longitude, and in upcoming days, the solar orbiter can even get a better heliocentric latitude as well. So every time we do validation, without doing the uncertainty quantification, is not justified in a way that we will not know the whole system with respect to the uncertainty. in the system. So that's why, so the simultaneous characterization of this uncertainty as well as doing the multi-point validation is the objective. Let me go to the model system I am using. So as I mentioned earlier, so it's a modular approach to model the solar wind, starting with the flux transport model called ADOPT. So at the solar surface, uh, based on the HMI magnetograms data simulation, I start the photospheric boundary conditions, and then WSA model, which involves PFSS and PFCS model for the magnetic field extrapolation, and then the empirical formula for the velocity, and until 21.5 solar radii, and then the MS-FLUKSS, which is a MHD model developed at UAH for multiple purposes. Basically, it was developed for outer heliospheric interstellar medium and the solar wind interaction studies, but it has been used for inner heliospheric analysis quite a long time now. So it is very efficient to run multiple ensembles. So these are the overall architecture I'm using for the solar wind model. Let me start with the photospheric magnetic field map from ADOPT. So you can see here the global photospheric map, which is changing in time because I am running a simulation with the time-dependent boundary conditions, which is quasi-time dependent in terms of corona, but the photosphere, at least we can see the time-dependent modeling results here. So the central patch here actually looks like a with a high resolution patch. So this is from the data assimilation of HMI magnetograms from the near observation, basically from SDO, basically. So, but the otherwise the far side and the poles are actually simulated by the flux transport model, which involves the differential rotation, meridional flow, supergranular diffusion, and random flux emergence. So this is how it looks like typically with this color scaling, but we need the ensembles of ADOPT maps to quantify the uncertainty. So this is how it looks like at a time step. So here I'm wearing 12 different, the ensemble members from the ADOPT. So you can see the central patch remains the same as it is the simulation window, and the poles and the far side region changes its size of the cell. And so if you look at the different time steps, so it's even the lifetime also changes basically of the supergranular distributions. So yeah, originally the adapter provides provides publicly open maps, and they have a like they produce actually 12 different realization depending on the supergranular cells and sizes randomly chosen. And so this is a uh, basis for uncertainty quantification to start with the the ensembles provided by the ADOPT. And when you come to the coronal model, WSA, as I explained before, so we bring the photospheric magnetic field until 21.5 solar radii with the assumption of PFSS and PFCS. And you can see the time-dependent distributions of BR and VR here. So here this formula represents the WSA empirical formula. So you can see the time-dependent effects, like time-dependent variations on the photosphere, like within 1 month of period actually. So, but yeah, it is hardly seen in the BR map, depending on the solar cycle phase. We are at the like 20. This is 2020, so it's a rising phase of the solar cycle. So, and this is how it looks like for the ensemble. So when we propagate our photospheric uncertainty to corona, so this is how the coronal solutions varies for BR and VR. So as you can see, for each ensemble member, the BR map shows the change in tilt and the position of the current sheet, but for the velocity, it makes a significant difference, or it makes a difference in all locations basically. So, and the size of this slow solar wind patch and the fast solar wind blobs, and so many things change just because of the supergranular distributions changes, and because of that uncertainty. So we feed these time-dependent maps and these 12 ensemble members into our simulations. So coming to the MS-FLUKSS, so yeah, as I mentioned, this is ideal MHD solver with the 2 second order accurate in time and space, and so we solve it between like 0.1 AU to 1.1 AU to cover Earth, but it can be extended until any distance, even this is a multi-physics, multi-scale, multiple fluid model, so which can be applied to interstellar medium interactions as well with multiple fluids. So, but yeah, we derive the density and temperature after we get the velocity and the magnetic field with the different approaches, like directly using the correlation between velocity and the density and the velocity and the temperature. But here in this case, since I'm using multiple spacecraft in validation, and at the boundary, PSP was also there, and so I used the approach like constant kinetic energy and constant pressure to get the density and temperature. But this is overall the boundary condition looks like when I change the photospheric like ensemble members in the corona. So all four boundary conditions are like this, like radial velocity and the density anti-correlated, and the temperature is most correlated with the velocity. And this is what we feed to the MHD model. But how to validate this complex MHD model? So this is not a single variable, semi-empirical, or a model to just directly validate and compare. So, but we have multiple variables, multiple points in the inner heliosphere. We are 3D modeler, so multiple realization due to the uncertainties, and multiple time scales, spacecraft, and user needs. But as we all know, the validation always involves some subjectivity, but yeah, I try to keep it as general as possible, just to provide this current status of the art models, how far are they in terms of modeling, by keeping all the coronal model parameters same, and MHD model parameters same. Basically, there is not much to change in MHD model, but boundary condition same, just varying the photospheric ensembles, just to see the impact of this photospheric ensemble. So in our recently published paper, so we tried to take advantage of the PSP and the solar orbiter era. So where we have chosen encounters from PSP, like fourth encounter to ninth encounter. So the reason for choosing these encounters was first three encounters were already validated from our models, like even before the third encounter itself, and then and considering the perihelion distance of PSP, like the PSP goes very close to the sun, like after P9, like P8 and P9 itself, like PSP reaches 15 solar radii close to the sun, and we were interested in validating that in the inner heliosphere. So we stopped at P9, and here I call P or P9 or P4 to P9 as a perihelion pass. So I define them as 12 days before the perihelion day, plus 15 plus 16 days after the perihelion day, like which cover roughly 27, 28 days to match with the solar rotation period, and it's a good time period to choose for validation. So here in this plot, the shaded regions of for each spacecraft trajectory shows the validation period I am going to show my results, and the dotted lines are basically plus or minus 30 days from the perihelion. So you can the benefit of this encounters was like this is the first time we are getting a we are getting opportunity to validate our models with different scenarios. Like, for example, in the P6, we have Sun-Earth line, and then the stereo was behind Earth, and TSP was covering like vast regions of longitudes, and then solar orbiter was in the far side. So at the same time, we are able to validate our results in the far side as well. What does that mean? Basically, it means like we are testing our flux transport models as well. Like how well are we doing with the flux transport model? Are we doing enough for this time period is good enough for just to maintain the flux transport model result, or something arises in the far side which affect the solution? So this kind of analysis can be done because of this very good configuration. So so we have done in this paper, we have done the validation, qualitative validation between the simulation and the observations in detail for all 6 encounters, considering the large scale structures like high speed stream and HCS. So for more details, please visit the paper. But today I'm going to talk about quantitative analysis mainly. So this is the second part of the second paper, basically. So here it looks like here it is the simulation results, and just as a glimpse for the perihelion 6. So the left two panels show the radial velocity in the equatorial plane for the left one. The first one and the second one is in the meridional plane or the vertical plane, and then the BR polarity of BR in the equatorial plane, and then in the meridional plane. So you can see the time-dependent effect on the equatorial solar wind solutions there, and also we can see the slow wind regions near the equator. This is a typical condition in the actually solar cycle minima, and the current sheet can be also seen. So in spacecraft testing. So this is how the validation looks like at multiple locations. Is there any question?
Yeah, can I ask now?
Yeah, you can ask.
Hi, Dinesh, this is Shatabdu. Thank you for this is a very detailed presentation. Thank you. Can you go back to your last slide?
This one?
Yeah.
Okay.
So I just wanted to know, what is the reason for this non-uniformity, these distortions in the BR polarity plot? Is this because of your heating equation?
No. You are asking about the third plot?
The third plot, yes.
Okay, so what happens, we are looking at the equatorial region, and then so during the minima, so we have our heliospheric current sheet. For example, if you look at the last plot, we have the current sheet like almost close to the equator. So right. What happens is like the slow wind or fast wind coming from the any of the hemisphere like just appears suddenly. So here it is hard to see, but it's like some of the regions are having a different polarity which appears suddenly here, but otherwise it is just the time dependent effect. Also makes the current sheet look like this, because every 12 hours we inject our boundary, and which can bring any new high speed stream or anything with a new polarity. So yeah, this is typical in terms of time dependent simulations. Yeah, it is time dependent effect with a different polarity.
Like if you are saying that this is because of the time dependence of the input conditions, then that would probably lead to your local formation of local current sheets, right? But
yes,
this was happening pretty far out.
No, I mean, actually, this is hard to see here. If you look at the video, we can clearly see, and this is just the polarity. So if you look at the BR, you would see better. So yeah, this needs close attention. But yeah, temperature doesn't affect, or thermodynamic nature doesn't affect anyway. So this is purely propagation of solar wind solutions from the boundary. So whatever happens in the inner heliosphere is just a propagation up to 21.5 solar radii. So here the white patch is actually 21.5 solar radii radius. So that is the inner boundary of MS-FLUKSS. But in the coronal, a lot of things happen, but within the inner heliosphere, it is just a propagation of whatever is coming from the boundary. So this is directly related to the boundary, whatever is coming, yeah, which is shown here. So, but
Okay.
yeah, it is reproduced, yeah, properly with all dependent effects. Thank you for the question. So, yeah, this is how it looks like at multiple locations without correcting for or without scaling for the dependence on the distance, but which is directly shown as whatever is observed from the spacecraft in RTN coordinates. So, for the vectors, and then the temperature, density, and the velocity, and IMF polarity as well. So, and this is the qualitative validation discussion we have made in the paper. So how well our model is capturing the high-speed stream and its arrival and its and HCS with the uncertainty quantified through these ensembles of photospheric magnetic fields. So, for example, you can see here in the at Earth. So we have captured the overall structure of HCS, high-speed stream, like with the fragmented streams, but we have captured the and part of the high-speed stream actually accurately, but the initial part is different. This depends on the boundary conditions, and then even the coronal holes, which has fed into our coronal model. So, I mean, into our MHD model. So, but you can see the ensemble models can create a difference in the arrival time of high-speed streams at Earth, and at the same time, for PSP, the variations in velocity is like very much compared to other locations because of the photospheric ensembles, and then you can see the difference in polarities captured due to this ensemble. So, as I mentioned before, the HCS locations changes due to this photospheric uncertainty. So that makes it problematic in terms of polarity reconstruction. So, but at least one of the ensemble member is capturing the polarity out of all ensemble members. So this is the importance of having an ensemble member which demonstrate our uncertainty, so that we will not miss out all possible cases. So this is the advantage over actually having the ensemble member simulations, or single simulation basically. But if you see at the solar orbiter, like it's completely off, like which in simulation shows here it's the orange lines are the simulation basically. So simulation shows very fast wind, but solar wind was observed, very slow solar wind was observed. But this can be justified saying, okay, at least solar orbiter was always in the far side, and so whatever the flux transport or the coronal model optimization may be not enough. So it is there are many reasons, but here I wanted to just see how does this look like, and detailed validation of qualitative all these structures are done in the paper. So, but let me go to the quantitative performance evaluation. So to quantitatively evaluate like how well our model is doing at multiple locations for different variables, different cases, in a normalized fashion, like to clearly compare between them, like where are we doing well or not. So we need to first remove the radial dependence on this of the solutions. Basically, as we know, the PSP is very close to the sun sometimes, and then it crosses a lot of heliocentric radius, and other spacecraft like Stereo and Earth is always near 1 AU, but solar orbiter also crosses multiple solar radius and multiple heliocentric distance. But in this case, P6, it is just near 1 AU, but in the far side, the solar orbiter. So basically, we scale each variables like other than velocity to remove this radial dependency, and then so we will be on the same scale, same level. So now we can compare and validate and create metric, calculate metrics, and so compare our simulation results. So, but is it that simple just to calculate individual metrics? But as I mentioned before, yes, we are dealing with 3D multiple points and multiple variables, but at the same time, we have multiple properties like embedded into our system. Like solar wind is characterized with multiple like high-speed stream, arrival time of it, and high HCS, and like many more. So to capture all these properties in a statistical sense through these metrics is not a trivial thing. So yeah, we again learned from this hydrology department basically. So the Taylor in 2001 created a very beautiful diagram. So which is a combination of the RMSC, which is a centered pattern RMSC, so which is the RMSC after removing the bias, and then the standard deviation of observed values and standard deviation of simulated values, and the correlation coefficient. One can plot all these four parameters in a one diagram, which is basically in the polar coordinate system. So in the radial here in the left side, I'm giving an example of this diagram. Basically in the radial direction, so we have the standard deviation, radial axis is, and the angle is actually correlation coefficient is described here. And this contours and this star is the reference point. And this is the observation, which has like a standard deviation of 1, and then because this is normalized. This is not normalized, but this is not a normalized one. This is a very in the natural units, so standard deviation of like 1.7 ish. So and this is the observed standard deviation. This dotted line represents the observed standard deviation. So and this contour starting like centered centered at this star actually represents the random RMSC or the centered pattern RMSC. So basically, you can see all four and correlation coefficient, all four statistics in one plot. So what it shows, the takeaway is these numbers are actually the model results. So this is like comparing our simulations in one plot, all ensemble members. So these are 12 ensemble members from the photospheric magnetogram ensemble, and what it says is whichever is closest to the star point, like in terms of radial distance, so that is the best model, or that is the closest to the observation. So and also if the model results are very close to this standard deviation curve, that shows that our model is capturing the variations in the observations properly. So and correlation coefficient is anyway shown like sixth model is like ensemble member is like showing a 0.7 or like near 0.6 or 0.55 correlation coefficient. So and you can show the bias as well, like the systematic error. So in the colors, so if it is reddish and then bluish, it's like positive or negative biases. So this is a diagnostic tool. Like just producing one RMSC might give some answers, but we will not know where exactly this error is coming from. So this is a diagnostics tool. So this can be exploited to understand our actually modeling setup. So for that, using the advantage of this Taylor diagram and its normalized nature of Taylor diagram, what one can do is comprehensively understand the validation. So like by compressing like multiple aspects into one diagram. So here I showed just the simulation result just for one variable at one location, but here I'm showing performance across multiple variables at a particular location. Like at PSP, okay, what's the relative validation for variables? So I can plot this in a normalized space. So you have standard deviation 1 and all the scaling factors which has been used for normalization. And this is based on the standard deviation of the observed values for each variable. So, and you can see here basically the BR, BR and the velocity. So velocity is in the red color, and which is away from the standard deviation of the observation. So that shows that like PSP was actually observing a very high variable speed, and which is not exactly same as the observed variations. But other three variables are capturing the variations, but they are not capturing the correlation, having the correlation coefficient accurately. And RMSC, random RMSC was actually smaller for other variables, but for velocity it is not the case. So this way we can digest the validation results into a single diagram, and we can see the earth as well, like velocity was reproduced well, but other variables like BR and density was not reproduced well, but like temperature was missing completely the variation, so it was almost flat. So at Earth, so you can see the full time series comparison in this Taylor diagram to understand what's happening. For example, it's solar orbiter again, so the velocity is like way off from the observed velocity, right? So this can be seen in the Taylor diagram easily, like which is like away from the standard deviation. So this is how we can compare, like, and our results show that. So this performance is inconsistent. Like it is not for all the variables at the same location, as well as performance across multiple points. For example, for a variable. So, and here I'm showing the radial magnetic field and 4 variables at, by combining all 4 locations again in the normalized space. So you can see for a radial magnetic field, these results are scattered near 0.2, and so the correlation coefficient is very bad. And this is also because BR has a polarity component. So if you miss a polarity, so you will be like anti-correlated or you are badly correlated, right? So this is having a penalty for that. And for velocity, so the speed, you can see like how we are doing for the stereo and Earth. We are reproducing well at 1 AU, but we are doing badly for PSP and solar orbiter. Like that shows that either flux transport model is not enough to capture far side what's happening, or even the coronal optimization, which is made for Earth, was not useful for even solar orbiter or even all other spaces. So it is just a 1-point optimization. Even if you are doing this MHD modeling, but with the semi-empiric models like the WSA, we should be careful. So and density and temperature follows the similar stuff. But and due to the nature of this normalized diagram, so we can even compare multiple perihelions like in a same diagram. So what it shows, so for the radial magnetic field, you can see the scatter of the result across the Taylor diagram with like -0.5 correlation coefficient to like plus 0.7, 0.8 correlation coefficient. So, and these are the encounters, like 2 different encounters where we did the polarity badly. So that is why we are getting like anti-correlated almost. But in some of the cases, the velocities reproduce very well with the correlation coefficient and even variation. But yeah, we are missing some high-speed streams, and that affects the result. So this way we can see which encounter is doing well, and we can dig down like deeper into the problem or understand the evaluation. This is a good approach in terms of analyzing these impacts, relative variations in the performance. So this is for Earth and stereo A. Again, the scatter is different. So what it shows is basically these performances are like inconsistent. They are not like predictable that easily. Like if you are doing well at Earth, so you are doing at stereo or other spacecraft is not understood. Like you are using a model which is optimized for Earth, but can you use it for Mars straightforwardly? No. This is the importance of this result and the multi-spacecraft analysis. But there is a discussion in the literature saying that, okay, since these models are computationally expensive, one has to reduce this uncertainty by just choosing a best member in the background first and then apply a CME model to do the propagation. But can we really do that, like choosing the best realization from these ensembles? Is it possible just to see that? Like we can see the result here. So plotted for each variable at each locations, you can see the, as I mentioned earlier, so the closest member here is the best ensemble member. But are we having a consistent best ensemble member at multiple variables for multiple variables at a particular location? No. So basically, we are having a different ensemble member being the best member at a same location. So this is again another inconsistency between the ensemble members. So we have to deal with all the ensemble members until and unless we check its impact on the downstream applications. We cannot disregard just, okay, this is best for this period, so I can choose a best ensemble member. But to do it in a one metric fashion, like a skill score. So we calculated a Taylor skill score based on the correlation coefficient and standard deviation of observation and simulation. So here I am plotting this Taylor skill score as a heat map for different variables. And for each variable, I am plotting for different probes and its averaged value, and for all the ensemble members. So, and highlighted borders here shows actually the best ensemble member for each case. So what does this mean? So basically for PSP, so the sixth ensemble member is the best ensemble member, and for Earth it is the seventh, and the solar orbit is seventh, and the average on average it is sixth. And if you see the first takeaway is like in all these cases, these best ensemble members are scattered. So they are not consistent. That is one thing. And second one is, out of all four variables, like for velocity, you have a better skill score, and that too for near Earth observations, like near 1 AU observation, like at Earth and stereo A. So which is way better than other locations. And as I mentioned already, the solar orbiter and the PSP were having a different longitudinal coverage, and also the complexity in the coronal optimization doesn't work that's easily for the other locations maybe. So this is important to, while choosing the best realization, this is not that straightforward. But then, okay, ultimate question is, what is the maximum performance limit? So can we really worry about improving these results, considering our considering our constraints like the uncertainty in the boundary conditions? So just to check that, so what I plotted here is the Taylor diagram, which is like a comparison between observation and modeling. But in this case, okay, what is the best member actually? What is the best solution is defined as? So the best solution is defined as a member which is drawn from the same distribution as the simulated ensemble, basically. So if our observation just falls within the ensemble member distribution, then we can say, okay, we are having at least the best result. But assuming that what I plotted here is like assuming each ensemble member as the reference first, and I plot other one as a simulation point. So this way I will get a combination of 12C2, and I plot all the combinations here. So what it gives is the maximum performance limit. Like assuming if your own ensemble member as reference, what is the best performance you get, like for each cases. So for example, for Earth, for velocity, you can reach up to like 0.98 correlation coefficient, considering the uncertainty you have and through your ensemble members. But for PSP, so you can get maximum 0.9 for this at least time period. So this varies for different time period, and so it is a data-driven simulation. So, and for Earth, for radial magnetic field, it is different. For Earth, for temperature, it is different, and for stereo and solar orbiter, it is different. But this gives one realistic expectation for our models to compare. Okay, considering the limitations of these uncertainties, so how far are we doing actually? So is it like improvable, or it is saturated? So we need something else, or we are missing some physics, so we need to add some physics to the model, or in the boundary conditions, or coronal part. So this is a direction in terms of that. But last result actually is about distribution of uncertainty. Okay, so we know that the photospheric uncertainty is coming from the far side and the polar regions, but how is this uncertainty is distributed after it propagates to the inner heliosphere, basically? So to do that, like we have plotted the ensemble standard deviation just for each variable for different encounters I validated for different spacecraft. So as a Venn diagram. So here what you can see is like for Earth, the scatter is small and almost standard, like uniform. But for PSP and solar orbiter, it is like more scattered, and so it has a very long range distribution. So this is because of the location of longitude or optimization issue. But this is purely coming from the photospheric uncertainty. So what it says is like even because there are some papers in literature, so they say that these adapt ensemble members are not creating enough distributions at Earth, and that is true. But at other locations, it is not the case. So they are creating a very big uncertainty, like velocity for PSP, like 100 kilometer per second variations in the velocity is like very big. Like even for CME, this is an important aspect actually. So we have seen some other simulations, so how the background uncertainty affects our CME. So in that way, so this is yeah, this is the case. Like for each for different locations, this affects like this is different. The distribution is so. Finally, to summarize, yeah, we could predict the solar wind background at different heliospheric locations reasonably well, but we still have variable dependent performance at single probe because the model ensemble shows inconsistent performance across different solar wind variables when evaluated at a single probe location, and this is the same thing. Even inconsistency is there for a given variable for multiple different locations. And we have member-wise inconsistency. Of course, this is the uncertainty we are dealing with, and then the member-wise inconsistency across locations. And then we have some empirical upper bound, which can be calculated for any set of ensemble members through this way, just to check yeah, what is the saturation limit. And then the non-uniform distribution of uncertainties and comparison of this ensemble spread distribution shows that this changes across multiple locations and variables. So we need to take care of these uncertainties and then calculate all other downstream applications based on the solar wind background. So thank you. Any questions, please?
Is there any questions? Audience, please.
Oh, sorry, I stopped sharing. Let me know.
Let me see. Ketke, yeah, and go on.
Yeah, thank you for the nice presentation. Maybe just a comment. As you said that PSP and Solar Orbiter did not model well, the modeling results did not match with the PSP and Solar Orbiter observations. And I also think like it's a problem with the adapt magnetic maps, because I also did the simulation with the adapt magnetic maps, and I realized that we have like 12 realizations, right? So all the 12 realizations actually give like very different outputs sometimes, and you need to check that. And also like the magnetic map that you showed with the adapt, and the polar regions look very symmetric, which might not be the case with the real observations, and that would have been created less accurate modeling results probably. I'm not sure.
Okay, thank you for your comments. Yeah, basically, it is hard to say directly without checking the coronal hole maps, or like what is your coronal model matters a lot as well. Because the same boundary conditions, if you replace with the fully physics-based model, the story will be different, and the WSA model, the story will be different, because the sensitivity of these boundaries for each coronal model is different. So, for example, in our WSA model, so this polar distribution is very sensitive because that can affect HCS locations drastically. So, and due to HCS locations, your polarity changes, and your like field line tracing changes, and your coronal hole boundary changes, and so it makes a difference. But as you mentioned about the polar distribution, we don't know, because we have large uncertainty near the limb, first of all, and only like for some time we observe one pole, and then we don't know.
Exactly. I also observed that, but with the Gong magnetic map, actually, not with the adapt, we only had like one polarity, and that was very weird, and it was messing up with all the solar wind simulations. But yes, you need to check this magnetic maps very carefully. That's what I think.
But what you said about this, like for PSP, the variation change, like so adapt maps change, I mean, give drastically different results. That is not a negative thing actually. So that is very important. That shows that like these results are sensitive for different locations. So if PSP is somewhere and then its solution is like varying depending on the photospheric uncertainty, that shows something like we need to take care of this uncertainty. So we should not be worried that solutions are different. We should be worried that we did not take care of this before, and we need to take care if we are doing like a CME simulation on top of it. So these are inherent uncertainties. So we cannot solve it until we observe it properly and okay, say this is the correct ensemble, correct magnetic field map. So there is no ground truth to compare our photospheric maps. That is the thing. So until we solve this, we cannot solve that. We cannot answer that firmly. So adapt is bad, or even any other maps are bad. And also when you solve the solution with the time-dependent boundary condition, story is different. And if you use the adapt map just for one character notation, one map, the story will be different. So we have lots of complexities while validating. We are very subjective, but it is good to express all of these complications. Yeah, thank you.
Yeah, thank you.
Is there any other questions? Okay, if there are no further questions, then we can wind up. Dinesh.
Okay. Yes.
It was a good talk, actually. Nice work.
Thank you. Thank you. Thank you for the opportunity.
Yeah, we wish you all the best for your such endeavors. All the best.
Sure.
Thank you. Thank you.
Thank you. Bye-bye.